All right, guys, so in the last section we talked about the phasor. We saw how to take a general sinusoid, perform a phasor transform on it by essentially only taking the magnitude of the sinusoid as well as taking the phase constant, leaving the temporal portion out of it. We also talked very briefly about how to take the inverse phasor transform. Now, the whole reason why the phasor and the inverse phasor transform is so useful is for the following section is that we can rewrite the IV characteristics for three passive elements, namely the resistor, the inductor, and the capacitor. We can rewrite them in phasor form and then carry out meaningful calculations based on the transform IV characteristics of these three elements. So in the next few videos, what I want to do is I want to take a look at each one of these passive elements and rewrite the IV characteristics in phasor form. And I want to start with the resistor. So this is the passive circuit elements. In what we call in the frequency domain. And the goal is going to be to rewrite the IV characteristics for the resistor, the inductor, and the capacitor in phasor form. This is assuming that either the voltage or the current are perfect sinusoids. And again, let's begin with the first part. Let's take a look at the resistor and Ohm's law. So suppose that we have a resistor here, like this, where we have an applied voltage, which in general is varying as a function of time, and there's a current that flows in that direction from high voltage down to low voltage. Now, we know that by Ohm's law, no matter what these functions are, the relationship between the voltage and the current is such that the voltage as a function of time is equal to the resistance times the current. Right? Now, let's assume, because we are, after all, working with sinusoidal sources, let's assume that the current takes on the following form. It has some magnitude, I sub m, and the sinusoid is of the form cosine omega t plus theta sub I. The I there is just to remind us that this is for the current. Then by Ohm's law, the voltage, which is a function of time, right? All I have to do is multiply that by the resistance, right? So this is I sub m times R, or if you want to be a little bit more proper and a little bit more careful for those eagle-eyed students, this is R times I sub m times the cosine of omega t plus phi sub I. Now, notice that on the opposite side of v of t, since the current is a sinusoid, well, the voltage also has to be a sinusoid, and it's of the form v sub m times the cosine of omega t plus theta sub b. Right. And now one of the things that I can do is I can perform a phasor transform on both of these. So right here, I'm going to perform a phasor transform. And the way I'm going to do it is on the left-hand side, I'm picking off the magnitude. I'm picking off the angle. So this is V sub m times e to the j theta v. And on this side, I'm picking off the magnitude, I'm picking off the angle. So here I have r I sub m times e to the j theta I like this. And notice that this part right here, right, well, that is the voltage phasor, the full voltage phasor, while this part right here is the full current phasor. So this is also R times I like this. Even though this looks to be absolutely identical to Ohm's law, which we have up here, right, it is very, very slightly different in the sense that this is generalized for all possible functions of the current and the voltage, while this one is the phasor equivalent. Of Ohm's law. And notice that it pretty much has the same mathematical form.